Section 2.5 and 2.6. 2.5 is more mathematical than 2.6. 2.6, we're going to start learning how to name compounds that only involve nonmetals. But 2.5 is very heavy on the math. We're going to learn how to calculate the average atomic mass. Now, one of the most important, or not important, but one of the most missed things that students do when they're making isotopic symbols is they will think that the periodic table, those decimal numbers that's on the periodic table, are the mass numbers. And they're not the mass numbers. Mass number tells the number of protons, the plus neutrons in the nucleus of an atom. However, back to our example of tritium and hydrogen and deuterium, there are 3 different isotopes that we have for hydrogen. And yet, if we were to include every single isotope of every single element and write their mass number on the periodic table and show them all, think how large the periodic table would be. You'd have to have 3 isotopes for hydrogen. You'd have to have 2 isotopes for carbon. There are 3 isotopes for oxygen. There are so many isotopes for different elements. The periodic table would be so large and so confusing. And some of those isotopes, like tritium, they're such tiny, tiny amounts. When's the last time you ran into any tritium? You don't even know what tritium is, a lot of you probably. And we don't, on a daily basis, even run into deuterium. And you probably wouldn't unless you just happen to work in a nuclear power plant where they need deuterium to make heavy water. So we don't think about all of the different isotopes of the different elements. However, when we're thinking about averages, we do need to think about what is the average atomic mass. And that's exactly what number they put on the periodic table for hydrogen. So they calculated, well, what percent of all the hydrogen out there in the world is hydrogen 1? What percent of all the hydrogen out there in the world is hydrogen 2 or deuterium? And what percent of all the hydrogen out there in the world is hydrogen 3, which is tritium? And then they calculated the mass of each of those and multiplied it times its percentage. And that's the number that they put on the periodic table as the average atomic mass. So let's talk a little bit more about that. And let's look at what I'm talking about right quick. According to international agreement, the atomic mass is recorded on the periodic table not in grams but in a little tiny unit called atomic mass unit. And that is the mass of a single atom. Not a bunch of atoms, but a single atom. And it's so tiny that you can't measure it in grams or pounds or ounces. It needed its very own unit. And so they came up with the atomic mass unit, which is very original. It is a unit that's used to measure atoms. Therefore, they came up with atomic for atoms, mass unit. So, and they defined it, but basically, it's a unit that we use to measure tiny, tiny masses like masses of atoms. But they made sure to translate it into units that we could use to also measure grams, which we're going to talk about later. Okay, so let's look at how you calculate it. And so I'm not going to spend much time on this slide at all. I want to just show you exactly how you're going to have to go through calculating the atomic mass for something, okay? Let me see if I can find you an example. There we go. I'm waiting for the slide to... The book talks about this scale right here, but it's not going to be near as important as actually being able to do this right here. Okay, here's a sample problem that you're going to be able to find in your book on page 51 in your text. It talks about oxygen is the most abundant element in the Earth's crust and in our human body. And it tells you that we have these 3 isotopes of oxygen, Now look at the most highest percent of it. Almost all of the oxygen that's out there is oxygen 16. And then there's oxygen 17, and then there's oxygen 18. Okay? And it gives you the percents of them. So let me go to drawing mode here and show you how that you'd go about calculating the average atomic mass that they put on the periodic table. All in the world they do is they say, okay, 99.757% of all the oxygen out there has that mass. So they said 15.9949, that's its mass. And then this is the percent. And you know, to multiply a percent, you have to first change it to a decimal. So they said 0.9957. Oh, how about 99757? And let me get a calculator here. They got a calculator and they did that math. They said 15.9949 times 0.99757, and they got that answer, and that is 15.5. Oh goodness, 956. 956. And then they did the exact same thing to this. Now look carefully on this. For this one, we're going to have to say 0.00038 times it by the 16.9991. And when we do that, 0.00038 times 16.9991, we get 0.00646, which is close enough to 65. Okay, and then you're going to do the exact same thing with this oxygen 18. There's only 0.205% of that, so we're going to say 0.00205% times its atomic mass, which is 17.9992. We're going to do that math. 17 9992 times 0.00205, and that is 0.0369. And then you just add those three together. And when you add those three numbers together, I get anyway, 15.999, which is exactly, I get 15.99939, which is 15.9994, which is what they have on the periodic table. I got 15.99939 something AMU, which on the periodic table, if you look at oxygen number 8, it's got 15.9994 on the periodic table that I'm looking at. Okay? That is how they get those numbers, and that is what you're going to be asked to do as well, is to calculate the atomic mass for those different elements. Okay? And it shows you how you're going to do that, and since it gives you the solution here on the next screen, I'm waiting for the screen. There is a slight delay always. And since this is so close to 15.999, typically you round atomic masses to 16. And remember how in Chapter 1 we learned how to do a conversion factor, and we learned how to do dimensional analysis? You will use these later as conversion factors, because one atom has a mass of 16.00 AMUs. So if I asked you what would be the mass of, say, 28 atoms, then you would be able to use this conversion factor. One atom is 16.00 AMU. You'll be able to tell me how many AMU 28 atoms would be, or some other conversion that we'll learn how to do at a later date. Okay? Now let's move on to section 2.6, which talks about what is a molecule and a molecular compound. And I may break this into two segments, but you do need to know what molecular compounds are and molecular formulas, and they do come from non-metals. And remember, non-metals are on the right-hand side. There are not a whole lot of them, but you do need to know what a molecule is. A molecule is when you combine chemically two atoms and they are held together by sharing their electrons. This is called a covalent. Covalent, I think of covalent, has like a share, has that long A, so their electrons are being shared. Their electrons are being shared, and you need to understand that. And then there's a hydrogen molecule is an example, H2. And I want you to think about why these happen and why these occur. Remember, I told you that the most important elements that are on the entire chart are the noble gases, because they are by far the most stable. And the reason that they're most stable is because they have a full outer energy level. Okay? And so let's just take hydrogen. We're going to draw what's called an electron dot structure, which shows hydrogen's one valence electron. It only has one electron, and it wants to have two so that it can be like its closest noble gas, helium. So if you got two hydrogen atoms together and you brought them close together and you put those two electrons in between them so that they're both sharing that electron, they can both feel that electron pair that's being shared, so that it's more like this going on, this situation. Now this hydrogen is feeling the effect of those two electrons, as is this one, and they're both feeling like helium, which has two electrons. Now mind you, they are not turning into helium, but they are feeling as if they have the two electrons that helium has. And so they are acting like helium. And this makes them especially stable. And this kind of sharing this electron pair is called a covalent bond, a covalent chemical bond. And it makes this electron pair stable. And that's why it happens. And electrons that share a pair of electrons like this, and it's so stable that they will never be found alone in nature, are called diatomic molecules. And as elementary as it may sound, the way that I remember this is from an old college professor that once told me about a German family called the Brinkelhoffs. And they had 7 sets of twins, and they were called, their last name was Brinkelhoff. And these are them right there: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These 7 elements will never, ever, ever be found alone in nature. They will always pair up and form diatomic elements called, so these are your 7 diatomic molecules, never found alone in nature. Their smallest piece is not going to be an atom. It's always going to be a molecule. Always. All right. So these are called, this textbook, I personally had never heard them called this before this particular textbook, but Dr. Burdge, that wrote this textbook, she calls these homonuclear diatomics, because the atoms are the same, like hydrogen H2, oxygen O2. They're homonuclear, the same element. And then she also calls others heteronuclear, where you could have CO, like carbon monoxide. That would be a diatomic as well, because it has 2 different atoms. And then we're going to learn about something called polyatomics, but I may do that in a different lecture. You also need to know the word chemical formula. Chemical formula just talks about what atoms and what proportions those atoms are in a substance, any substance, like H2O is the chemical formula for water. And then also a molecular formula shows the exact numbers of atoms. And then allotrope is one of those kind of just little known words, but the most common example of an allotrope that I can give you is for carbon. Carbon talks about the different forms of the same element. For example, carbon can exist in 3 distinct forms. Graphite is a form of carbon. Diamond is a form of carbon, but diamond and graphite, even though they're both carbon, they are extremely different. Diamond is one of the hardest known substances, and yet graphite is what pencil leads are made out of. So it's very soft, and it's all about how those carbon atoms are arranged when they layer themselves. In diamonds, they arrange themselves in more pyramids, and in graphite, they lay flat. And so when you're writing with your pencil, they sheet off of each other. They just when you write and you push your pencil lead along, you're pushing off a layer of carbon atoms. And yet diamonds, when they form in pyramids, and they're just, you can't break off a pyramid of diamond. So that makes them extremely hard and very, very different properties. But they're both made out of the exact same element of carbon. So they're called allotropes. And then there's something that's called, and we usually talk about this more in Chem 2, but there's something that's called a structural formula that doesn't just say what's in the element, what's in the compound, but how it's put together. I can tell you that a car is made out of, rubber and fiberglass and, but if I don't show you how it's put together, there's lots of different things that are made out of the same thing, but how it's put together. And so these are what it's showing you, the different ways that you can write water. The molecular formula for water is H2O, and yet these 2 red balls are different ways that you can write the structural formula, the ball and stick method for it. All right. And then binary molecular compounds. Binary, bi meaning 2. So binary molecular compounds are made of 2 different elements, such as water is a binary molecular compound because it's just got hydrogen and oxygen in it. So that's a very common example of a binary molecular compound. But it can exist in 2 forms that we talked about a little earlier, like water and hydrogen peroxide. Things like also carbon monoxide versus carbon dioxide. Those are also binary because they're made out of 2 elements only, carbon and oxygen. So we're going to learn how to name those now. But I think that I'm not going to do that using these slides. I think I want to veer off of the slides and do this using my Doceri tablet instead of doing it using the slides. But I do want you to know that they are all going to be named exactly the same way. You use prefixes and they're all going to end in the word IDE. But I do think that I can do a little bit better job if I don't just stick to these slides. And my video is getting so long, so I'd rather want you to sit on these prefixes, but I think I'm going to stop and do a different video.